large ship, powerful tugs exert great force against the water by their churning propellers. The same amount of force is also exerted against the propeller shaft of each tug. This force along the propeller shaft is called thrust. When the tug is developing maximum power, its propeller thrust amounts to many thousands of pounds. But that's nothing compared to the thrust created by the propellers of a large ship at full speed. On a carrier of this size, just one propeller may transmit a thrust of more than 500,000 pounds along its shaft. If the thrust of the propeller shaft bore directly against the engine or its reduction gears, the results would be disastrous. Bearings of special design are required to transmit tremendous running thrust loads directly to the hull of the ship. Not only the propeller shaft, but various other types of machinery aboard ship present the same tough problem of transmitting or absorbing thrust. In a main propulsion turbine, steam blasts through the blades in these wheels to make them revolve at high speeds. The steam tends to push the bladed wheels against the stationary parts, which fit with close tolerances between the wheels. Bearings are needed to absorb this thrust and maintain the exact operating position of the blades. Thrust also is exerted along the shafts of a turbine-driven generator. If it were not absorbed, the turbine, gear, and generator elements would be jammed against the casings and damaged. The same problem of thrust is presented by forced draft blowers. The film will show how the problem of thrust is solved effectively with a Kingsbury thrust bearing and demonstrate the principle on which the Kingsbury thrust bearing is based. Let's analyze the problem. This rotating propeller shaft exerts thrust, and at the same time, it exerts radial load because of its weight, which is a lesser force. This radial load is at right angles to the thrust. The radial load is absorbed effectively by a radial bearing, commonly known as a journal bearing. The turning shaft is bathed in oil. Oil adhering to the turning shaft is drawn between the shaft and the bearing surface. A turning shaft shifts slightly off-center under stress, and this allows the formation of a wedge-shaped film of oil. Because fresh oil is constantly drawn into the entering side of the wedge, the turning shaft never rubs on the bearing surface. However, when an axial or thrust load is exerted on the shaft, the journal bearing alone will not do the job. To contain the thrust, a collar must be provided on the turning shaft to transmit the thrust to a stationary bearing surface in a housing which positions the shaft. Unlike the surfaces in the journal bearing, these bearing surfaces are flat and parallel. Under application of a large amount of thrust, the lubricant tends to squeeze out, leaving the bearing unprotected. An example of this sort of stationary bearing surface is the thrust washer which is employed in the swivel chair. As we all know, even the weight of a man in a swivel chair will eventually squeeze out the lubricant. The thrust washer may be made more effective by putting grooves in it, which tend to introduce fresh oil between the moving and the stationary parts. However, when a heavy thrust load is applied, the lubricant is squeezed out, just as in the case of the simple washer, and metallic rubbing between the moving and stationary surfaces results. A study of the journal bearing proves that the oil wedge is the key to its successful operation. The solution to thrust is a bearing designed to create the same oil wedge, continuously maintained to float the thrust force free of any metal contact. Let's try an experiment which will demonstrate the principles involved in the problem. Here is a flat surface covered with lubricant, a flat plate, and a weight which will represent thrust load. These are the same flat parallel bearing surfaces that stymied us with the thrust washer. But watch. When the weighted plate moves, it tilts up, and an oil wedge forms between the plate and the flat surface. This wedge fully supports the load. When the direction of movement is reversed, the oil wedge forms from the other side. Now, let's see what happens when the weighted plate is supported on stationary pivoted segments or shoes. Now, when the weighted plate is moved, the pivoted shoes, rather than the plate, tilt to form oil wedges. Like the weighted plate, the pivoted shoes work well in either direction and adjust automatically. These shoes provide important advantages. If we arrange the pivoted shoes in a circle like a segmented washer and change the weighted plate to a rotating shaft with thrust collar to apply the load to the shoes, we have the basic parts of the Kingsbury thrust bearing. Before the shaft starts to rotate, the shoes are parallel to the collar and separated only by a thin film of oil. Oil adhering to the rotating collar is drawn between the collar and the pivoted shoes, tilting the shoes and forming supporting wedges of oil. Observe that the bearing surfaces never touch, and the entire running thrust load is floated on a wedge of oil. Note that the angle of the pivoted shoes automatically adjusts to the speed of rotation and to the thrust load. The angle is greatly exaggerated here. The bearing thrust load capacity increases as the speed of shaft rotation increases. If the bearing is kept perfectly clean and the oil supply is properly cooled and filtered, the bearing should operate indefinitely without measurable wear. This is the basic principle of every Kingsbury thrust bearing. The alignment of the bearing housing and the shaft is carefully adjusted on installation, but the thickness of individual shoes may vary minutely, and during operation, the bearing housing and shaft are subject to unavoidable stress and strain. Some means must be provided to maintain alignment and equalize the load among the shoes while the bearing is in operation. There may be 2, 3, 4, 6, 8, or more shoes. The number of shoes and their arrangement in a Kingsbury thrust bearing is determined by the use for which the bearing is designed. The 2-shoe type is relatively simple in design and can be manually adjusted with jack screws. A 3-shoe bearing of this type provides automatic equalization and alignment during operation. 3 equally spaced shoes, like a tripod, will seek equal division of a thrust load. A spherical backing in the bearing housing allows the bearing to align itself for perfect equalization of the thrust load among the shoes. When the number of shoes is increased to 4 or more, the equalization problem must be solved in a different way. Automatic equalization and alignment is made possible by supporting the shoes on rocking or balancing parts called leveling plates. The assembly of shoes and leveling plates fits into a base ring. For demonstration purposes, let's pull out the assembly in a straight line. The leveling plates are arranged in 2 rows, upper and lower. The shoes rest on the upper leveling plates, which are free to move up and down under pressure from the shoes. When the thrust load on one shoe becomes greater than the thrust load on the other shoes, the shoe is depressed. This, in turn, depresses the upper leveling plate on which it rests. The edges of the upper leveling plate press down the edges of the 2 adjacent lower leveling plates, and, of course, the opposite edges tilt up, raising the upper leveling plates on either side. The shoes, which rest on these plates, are forced up, and thereby receive an increase in thrust load. This adjusting action continues through the entire series of leveling plates, which is really a system of overlapping seesaws or teeter-totters, until each shoe bears an equal load. In this case, only the weight of the collar is transmitting thrust, and the shoes are parallel to the collar. In operation, every shoe forms an oil wedge of equal thickness, even though the shoes may vary in thickness. The action of the leveling plates also allows self-alignment. Here, in great exaggeration of normal conditions, the collar is out of alignment with the bearing. The overlapping system of leveling plates operates in the same way to adjust the shoes in a plane parallel to the collar. In actual operation, the shoes adjust continuously to the minute flexure caused by the stress of running thrust loads. It must be remembered that these actions have been exaggerated for purposes of demonstration. Actually, the adjusting movement of the shoes and plates is minute. Here is a common type of Kingsbury thrust bearing taken from its housing in a feed pump. It is a 6-shoe bearing 5 inches in diameter. These are the shoes. They have a surface of soft babbitt metal. Each shoe pivots easily on a hardened steel button in its base. The shoes ride on the upper leveling plates. The upper plates are nested on the lower leveling plates. The entire assembly is set into the base ring. This protruding key fits into a slot in the bearing housing to position the base ring. This is a split type of base ring allowing radial assembly around a shaft. In reassembling a bearing, it is very important to distinguish a lower leveling plate from an upper. You can identify any lower plate by the blunt knife edge on which it rocks. Upper plates have a flat machined surface on which the shoe button rests. In this bearing, the bottom leveling plates have holes which fit over dowels in the base ring to position the plates while allowing them freedom to rock. These upper leveling plates have slots designed for screws which position the leveling plates while allowing them to tilt and move up and down. The shoes are positioned by these guides which fit into slots in the base ring. As assembled, the shoes have a great deal of play until the bearing is in position against the thrust collar. A single Kingsbury thrust bearing will work equally well with the collar rotating in either direction as long as the direction of thrust remains the same. However, if the direction of the thrust is reversed, the shaft will not stay in position unless another thrust bearing is provided for the other side of the collar. Double thrust bearings are always found where thrust is reversible. Double thrust bearings are not always matched. Where the reverse thrust load is smaller, you might find this arrangement: a 6-shoe bearing on one side of the collar for main thrust, and a 3-shoe bearing on the other side for the lesser reverse thrust. Some end play or clearance is always necessary in a Kingsbury thrust bearing to allow proper operation of the pivoted shoes. End play is the total amount of possible movement of the shaft and collar in either direction with the bearing in its housing. Excessive end play is not harmful as a rule to the thrust bearing itself, but could result in damage to the stationary and rotating parts located along the same shaft. Therefore, the proper end play is specified in the technical manual for the machinery in which the thrust bearing is installed. Usually, the technical manual also tells how to measure the amount of end play in the bearing. The importance of Kingsbury thrust bearings in Navy ships can be seen from the fact that a large carrier requires more than 90 of them, ranging from the huge bearings on the great propeller shafts to the 5-inch bearings in the pumps. The tremendous main propulsion thrusts of a carrier at full speed and the thrusts of its operating machinery are all floated on wedges of oil without mechanical rubbing of any kind. The basic principle of the Kingsbury thrust bearing.